Now in this lecture we would be looking into the topic hyperconjugation. Right, remember this is a part of mechanism of organic reactions. So we will look how through hyperconjugation displacement of electron takes place, and finally how bond gets polarized, right, how charges gets developed in the bond. Right, now before we look into hyperconjugation, there is something known as conjugation or conjugated system. Right, let's first understand in brief what is a conjugated system. Conjugated system you will learn when you will do the structure of benzene. Right, there we'll do that in detail. So conjugated system is basically, it is a system of alternate double and single bonds. Right, like in benzene, if this is the structure of benzene, we have this double bond, then you have single bond, then again double bond, in single bond, then you have again double bond. Right, so this is your conjugated system where you have alternate system of double and single bonds. Right, so this is your conjugated system, right, where you have alternate double and single bonds. Right, this is your conjugated system. Now we say that one thing we know, that double bonds, right, we did this in chemical bonding, that double bond is made up of one sigma bond and one pi bond. Right, so here if I'll draw this molecule in a different way, right, let's just draw it this way, it would be easier to show. Here you have a double bond, here you have a double bond, and here you have a double bond. So you have 3 double bonds and 3 single bonds, right? And this is a conjugated system of alternate double and single bonds. Now double bond is made up of p orbitals. By sidewise overlapping of p orbitals, a double bond is formed. Right, right, now what happens is, when you have this system of p orbitals, right, in conjugated systems you have a system of connected p orbitals, right, and in these connected p orbitals, in this system of p orbitals, electrons are moving. Right, so the electrons of these pi bonds, right, are moving in all p orbitals. Now these electrons doesn't belong to any one particular atom, they are moving. Right, and this is known as delocalized system of pi electrons, because the electrons of pi bonds are moving in these p orbitals, and these p orbitals are in same plane. Right, same plane means they all are aligned in the same plane so that the electrons can move, right, from one p orbital to another. It's not that you have one p orbital like this, the other p orbital is out of plane, right, then this electron would not be able to, electron in this p orbital would not be able to move electron in this orbital. Right, so these p orbitals should be in one plane like this, so that electron in this p orbital can move into this p orbital. Right, so we have a system of connected p orbitals in the same plane with delocalized pi electrons. Right, and this delocalization gives stability to the system. Right, so I'll just mention it over here. It's a conjugated system, alternate double and single bonds, right, and or a system of connected p orbitals, right, lying in the same plane, with delocalized pi electrons, right, which gives stability to the system. This delocalized system of pi electrons gives stability to the system or adds to the stability of the molecule. right? So just understand this, that we have these p orbitals and electrons are moving in this p orbital, right? But here we have a system of double and single bonds, right? And electrons are moving from one p orbital or from one pi bond to other pi bond, right? So here electrons in the pi bonds are interacting, right? Or pi bonds are interacting with one another through their electrons, right? This is your conjugated system. Now similar thing can be seen if you have a double bond, and to this double bond you have, to this unsaturated system you have this kind of arrangement, right? This is your alpha hydrocarbon, right? And this is your alpha hydrogen, right? Now when you have such a system, right, when you have such a system, when carbon hydrogen bond, right, is present at alpha position to an unsaturated system, right, you have this carbon hydrogen bond, it is at alpha position to this unsaturated system. Unsaturated system is where you have a double bond or a triple bond. Here you have a double bond, so this is an unsaturated system, and alpha carbon atom is the carbon atom next to the carbon atom of the double bond, right? And hydrogen connected to this alpha carbon atom are your alpha hydrogens. Now when adjacent to this double bond you have a carbon hydrogen bond, right, then similar effect is seen, right? In this effect the electrons of this sigma bond, this is a sigma bond, this is not a pi bond, right? The electrons of this sigma bond, right, here you have a pi bond, right? One bond would be like this, one is a sigma bond and one is a pi bond. One pi bond is formed by sidewise overlapping of these p orbitals, right? So when you have such a system where alpha carbon atom, where at alpha position to this double bond you have a CH bond, the electrons of this CH bond, right, will start interacting with this double bond, right? Basically the p orbitals of the double bond, right? Now this is little extension of this conjugated system, so we call it a hyperconjugation. Here the electrons are moving in the p orbitals, right? That is, the electrons of only pi bond are moving from one pi bond to another, right? They are moving from one p orbital to another, right? And all these are sigma, or all these p orbitals are of pi bonds. But here we see a little different thing. Here the electrons of the sigma bond are interacting with the pi bond, or they are interacting with the p orbital, right? Here we have the electrons of sigma bond interacting with the pi bond, right? Electrons of the sigma bond is interacting with the pi bond, which is similar to this but little different, right? So that is why we call it is different, because here we have a sigma bond and a pi bond interacting. Electrons of the sigma bond is interacting with that of the pi bond, right? So that is why we don't call it a conjugation, but we call it a hyperconjugation, right? Now just look at this, that when you have hydrogen here, you have carbon here, is a double bond. Now when these electron, right, will interact, right, electron density will move, right? Electron density, it's what it is basically doing is it is pushing electron towards the double bond, right? And when electrons from this CH bond, electrons from this sigma bond would be displaced towards this double bond, right, what will happen is this bond will get polarized, right? This bond will get polarized and it will look like somewhat like this. Let's draw it. Since the electrons of this bond is moved, right, so there is kind of no bond because bond is formed of electrons, right? Now when electrons are only moved, so there is kind of no bond, right? Right, this is how it will look like. You can draw this to electron. This has acquired a negative charge. Let's write it down as a negative charge, right? Because electrons of CH bond have moved towards the double bond, right? So this has resulted into the polarization of this double bond, right? By giving it a negative charge, this bond has become now polarized. Now, since you have this CH bond also, this CH bond also, right, which are at alpha position to this double bond, right? So electrons from this can also move towards double bond and polarize it. Electron from this bond also can move and polarize it, right? So you have number of structures. If suppose this electrons of this sigma bond will move, these sigma electrons will move, this is what you will get. Right now, even this can move. Right. So these are the structures, right, that results on hyperconjugation. When you have a sigma bond, a CH bond, right, adjacent to the carbon-carbon double bond, or the CH bond at alpha position to this double bond, right? So you need to have alpha hydrogens in order for a molecule to show hyperconjugation. Without alpha hydrogens, there would be no hyperconjugation, right? So without alpha hydrogens, because if there is no alpha hydrogens at this position, the bond delocalization will not take place, right? So without alpha hydrogens, no hyperconjugation, right? Now the other most important thing of hyperconjugation is, since you can see that this hydrogen atom, wherever the sigma electrons have delocalized into the p orbital of this pi bond, which is adjacent to this has developed a positive charge because there is no bond. Since electrons have moved, so there is no bond, but still this hydrogen is not free to move. This hydrogen is not free to move and is bound to the pi electron cloud, right? Here you have a pi bond, so due to this pi electron cloud, this hydrogen atom is bound to this molecule. It is not free to move, and since this hydrogen atom is bound with no bond, there is no bond because the sigma electrons have moved towards the double bond, right? So this hyperconjugation, we also call it as no bond resonance, because there is no bond between carbon and hydrogen, but still hydrogen is there. We call it as no bond resonance, right? This is your no bond resonance. Now you can easily see that how using hyperconjugation or via hyperconjugation the molecule, the organic molecule, get polarized, right? Because this is what we are looking into, this mechanism of organic reactions, that how molecule will develop polarities, right? So you can see when you have this kind of a system, you get the polarities will get developed. You have a negative charge here now. Right now a reagent can attack and can easily attack to this molecule because this molecule is polarized due to hyperconjugation, right? Remember the conditions that you need to have an alpha hydrogen. This is important, and it is also known as no bond resonance, right? I hope this is clear. Now let's just look into its orbital structure, right? Let's look into its orbital structure quickly. Right, if you have carbon, right, this is how the bonding occurs. This, if you want to draw the orbital structure of the CH bond, this is how it will look like. This is your 1s orbital of hydrogen, right, and this is your sp3 hybrid orbital of carbon, right. This is a CH bond, this one. Now adjacent to it you have this carbon of the double bond, right. Now suppose this is a carbocation, right, or let's say it's a carbon. You have a p orbital here, p orbital of this carbon atom, right. Now you have p orbital of this carbon atom. Between these two you have a pi bond, right. Now this orbital, right, this bond, CH bond, should be in plane of this p orbital. All these should be in same plane, so that electrons of CH bond can delocalize into this system of p orbitals. Like here in conjugation, all these p orbitals, I said they are in the same plane, right. That is why the pi electrons can move from one p orbital to another. They should be in the same plane. Here also this CH bond, right, or this orbital, the sp3 orbital and this overlapping of this h orbital, this should be in the same plane of this p orbital, so that electrons from sigma bond, these sigma electrons, can delocalize into this p orbital or pi bond, right. So this is basically known as delocalization, right, of sigma electrons into pi bond or into p orbital. For delocalization of sigma electrons into p orbitals of pi bond, adjacent pi bond, right, all the orbitals should be in the same plane. All these should be in the same plane, right, so that this interaction of sigma electrons with p orbitals can take place. Now suppose this is a carbocation, you don't have any electrons here, so this system of electrons can enter in this p orbitals due to hyperconjugation, right. This is your orbital diagram. We call it as orbital diagram, where we are showing that all orbitals are in same plane, right. I hope this is clear. This is an important effect, right. Just remember what is it, just know what is conjugation, right. And as I said that as it is due to this hyperconjugation is due to alpha hydrogen atoms. Without alpha hydrogen atoms there would be no hyperconjugation, right. So more is the number of alpha hydrogen atoms, more is your hyperconjugation activity. And this hyperconjugation activity, like this conjugation activity, is also a stabilizing factor. This gives stability to the molecule, right. It gives stability to the molecule. This delocalization of electrons gives stability to the molecule. It gives stability to the molecule, right. And more are the number of hydrogen atoms, more is the hyperconjugation activity and more is the stability. That is why the tertiary butyl cation, this will show maximum hyperconjugation activity, right, then this, right. So this will show the maximum hyperconjugation activity, right? Sorry. This is not the correct order. You have this system. If you have this kind of a system, this will show maximum hyperconjugation activity, where you have 3 CH bonds, right? And if you have, and this will decrease in this order. Now if you have here CH3, here H, here say you have this system, right? So this is your alpha hydrogen, right? And this is your, this is your alpha carbon atom, this is your alpha hydrogen atom, this is your alpha hydrogen atom. Here you have 3 alpha hydrogens, here you have 2 alpha hydrogens, right? If I move further, if I have 2 methyl groups attached to it, I have now only left with 1 alpha hydrogen. So hyperconjugation activity will decrease. Right now, suppose I take this, I have no alpha hydrogens. So this will show minimum hyperconjugation activity. Right? So hyperconjugation activity, like I said, will increase with increase in the number of alpha hydrogens. That is why we got this order. Here you have maximum number of alpha hydrogens, right? So here you have maximum hyperconjugation activity, right? I hope all this is clear. Thanks.